Good morning. So I think this is lecture 16. Let me pause for just 1 second. Good. So what we are starting today is chapter 2, which is on group theory. And this is called the basic theory of groups. And this is essentially what we're going to talk about for the rest of the semester. So let's just recall the fundamental definition. This a little bit. So a group G is a set with a binary operation. That means you have two things and you can associate a third thing to them. Sometimes the binary operation is called multiplication. Sometimes it's called addition. It could be called other things, but basically it's a function. So if you take a pair of elements, X and Y in the group, you can send that to some other element, XY in the group. And the simplest examples you learn about in elementary school, for example, addition of integers. Or addition of fractions, rational numbers. Or real numbers. Or complex numbers. Or matrices. So for each of these sets of the integers, the fractions, we usually write the integers as Z. The fractions or the rational numbers as Q. The real numbers as R. The complex numbers C. Matrices, sometimes we write R, Mn to be m by n matrices, or of course vectors. It's elements of Rn. So addition of numbers, vectors, matrices, these are all examples of a group operation, a binary operation in a group. And sometimes you have the binary operation of multiplication. So you have multiplication of non-zero rational numbers or fractions, or sometimes just the positive fractions, positive rationals, or the non-zero real numbers, non-zero complex numbers. These all turn out to be examples of groups. And even, for example, 2 by 2 matrices, right? Everyone's had linear algebra, that's a prerequisite, A, B, C, D, but you can multiply any 2 by 2 matrices, but you only have a group if they have, let's say, non-zero determinant. AD minus BC not equal to 0. So these are all examples of groups, but I need to give the formal definition of a group. I just started with the fact that a group is a set with some binary operation, and usually we don't even write down a symbol for the operations. We often do, though we often don't. Sometimes we just put the two symbols for the letters, the elements together, x times y. But a group is is a set with this binary operation that satisfies three fundamental properties. So let's just call the generic operation multiplication. So multiplication, or the binary operation in a group, satisfies three properties. That is, must satisfy these properties, or you don't have a group. So the first is associativity. That means if you take any three elements in the group, x, y, z, so for all elements x, y, and z in the group, x, y, you can multiply x and y times z is the same as if you multiply x with the product of y and z. So that's associativity. If you were writing the group operation as addition, you would write this as x plus y plus z equals x plus y plus z. So this is exactly the same property, but here I'm using multiplicative notation, and here I'm using additive notation. Second property is called the existence of an identity element. So there exists an element, let's call it E, in the group, such that EX and XE are equal to X for all X in the group. So that is, this identity element has the property that if you multiply any elements in the group X by the identity on the left or on the right, it just, you recover the original element. It doesn't change the element. And the third property is existence of inverses. Right? For all X in the group, there exists an element Y in the group such that XY is the identity and YX is the identity. And you can check that each of the examples of groups I started with above, addition and multiplication of real and complex numbers and so forth, they satisfy all of these properties. Well, if we do not require, so this is not a requirement for a group, that XY equals YX for all X and Y in the group. That is, we don't require that the order of multiplication doesn't matter. Okay. Now, some groups do have this property. So if XY equals YX for all X and Y in the group, then the group G is called commutative or abelian. These words are synonyms. So a commutative group or an abelian group is a group where the order of the multiplication of the group operation doesn't matter. So for example, suppose we take the rational numbers, Q, with addition as the binary operation. So 3/2 plus 1/5, you can add them. What do you get? You get something over 10. You get 15. I think you get 17 over 10. Right. So this is addition in the rationals. And the identity element, E, is just the number 0. 0 plus any fraction just recovers the fraction. And the inverse of 3/2 exists. In fact, the inverse of any number, A over B, the inverse exists. The inverse of any number A over B is minus A over B. So if you take 3/2, the inverse is minus 3/2, and when you add them, you get 0. And this group is abelian because 3/2 plus 1/5 is the same as 1/5 plus 3/2. They're both equal to 17 over 10. So the rational numbers with addition is an example. The set of rational numbers with addition is an example of an abelian group. A group that's not abelian is called non-abelian. And there's a group, we use this funny notation for it, SL2. Let's say SL2 Z. So this is going to be the set of all matrices A, B, C, D with A, B, C, and D integers, and determinant equal to 1. So for example, 7, 5, 4, 3 is an element in this set of matrices. So these are all 2 by 2 matrices. But it's not all 2 by 2 matrices. It's not even all 2 by 2 matrices with integer coordinates. It's just those 2 by 2 matrices with integer coordinates whose determinant is 1. So for this matrix, let's call this A, the determinant of A is 7 times 3 minus 4 times 5 is 21 minus 20 is 1. So this is an element in the group. And suppose I take another element in the group. So suppose I take B equal to 2, 1, 1, 1. Because this has determinant. The determinant of B is 2 times 1 minus 1 times 1 is 2 minus 1 is 1. And you're supposed to know how to multiply matrices. So if you multiply AB, that's 7, 5, 4, 3 times 2, 1, 1, 1. That's equal to 14 plus 5, 19. 7 plus 5, 12. 8 plus 3 is 11. And 4 plus 3 is 7. So if you multiply the matrices A and B, this is what you get. But if you multiply B and A, so you're multiplying in the opposite order, 2, 1, 1, 1 times 7, 5, 4, 3, we get 14 plus 4 is 18, 10 plus 3 is 13, 7 plus 4 is 11, and 5 plus 3 is 8. And if you look at these two matrices, they're completely different. So AB is different from BA. And the multiplication in this set is not abelian, it's not commutative. What is the identity element in this set? The identity is just the unit matrix, the matrix 1, 0, 0, 1, which we usually write as capital I. That's the identity. multiplying any matrix by the identity, this gives you the matrix. And you need to know that every matrix has an inverse in this group. Otherwise, it's not a group. So suppose, let's just take an example. Well, here's an example. If I take A to be 7, 5, 4, 3, what might the inverse be? So I could try to make a lucky guess, and what could it be? I think we'll try 3, 7 minus 5 minus 4. Let's see if this works. What is A times B in this case? That's 7, 5, 4, 3. 3 minus 5 minus 4, 7. And when I multiply, I get 21 minus 20, minus 35 plus 35, 12 minus 12, minus 20 plus 21. Lo and behold, I do get the identity. That's a miracle. So the inverse of this matrix is this matrix. And I should double check that it works in the opposite order. So let me do that, because it's a nice calculation to see. So suppose I multiply in the opposite order. I had said, let's see if I can show it here. B is 3 minus 5 minus 4, 7, 7, 5, 4, 3. When I multiply, again, I get 21 minus 20, 15 minus 15, minus 28 plus 28, minus 20 plus 21. I do get the identity. And in general, if AD minus BC equals 1, then the inverse of the matrix ABCD is the matrix D minus B minus C A. And just because this is really a very powerful statement, let me check. If I take ABCD times D minus C minus BA, when I do my matrix multiplication, I get AD minus BC minus AB plus AB, CD minus CD, minus BC plus AD. These are both AD minus BC, so they're 1, and this is CD minus CD, AB minus AB, that's 0. That's the identity. And if you multiply in the opposite order, the same miracle occurs. This is AD minus BC, BD minus BD, AC minus AC, AD minus BC. Again, that's the identity matrix. So we have this very beautiful example, SL2Z, which is the set of all matrices A, B, C, D with A, B, C, D integers, and determinant AD minus BC equal 1 is a group under the binary operation of matrix multiplication that is not abelian. So again, let me write down the definition or show you again the definition of a group. In a group, you have a binary operation, sometimes written multiplication, sometimes written addition, sometimes just written by the juxtaposition of the symbols. And you have a group of three properties satisfied. It's associative, there's an identity element, and every element has an inverse. And we're going to prove a lot of theorems about groups, and we'll start with two very basic ones that if I want to follow the numbering in the text, this is proposition 2.1.1, which is uniqueness of the identity. That is, not only does a group have an identity element, but the identity element is unique. How can we prove that? Well, proof. Let G be a group, and let two elements, let's call them E and E prime and G, satisfy the following properties. First of all, EX and XE equals X, so satisfy the following. For all elements X in the group, if you multiply X by E on the left or the right, you get by X. You get back X. And similarly, if you multiply X on the left or the right by E prime, you get by X. Get back X. So in this equation, we can write let X equal E. We have let X equal E prime. That's better. This says that E prime equals E prime E equals E. In this equation, if we let X equal E, we would get E prime E equals E prime equals E. Oops, equals E prime. We multiplying any element X by E recovers X. So if you choose X equal E prime, you get this. So for example, so this says that E prime is equal to E prime. But this says E prime equals E. In other words, E equals E prime. That's a proof, right? Of the uniqueness of the identity element, right? Another way of saying that would have simply been to look at this equation. If E is the identity, E prime is E prime. If E prime is an identity, E prime equals E. So E prime equals E. So not only does a group have an identity element, it has a unique identity element. The next fundamental observation, in fact, if you like, about groups, this is proposition 2.1.2, is uniqueness of inverses. We know every element in a group has an inverse, and I'm going to show the inverse is unique. So let X be in G, let Y in G satisfy the condition of an inverse, XY equals YX equals the identity. And let Z in G also satisfy the condition of an inverse, x times z and z times x equals E. And I must show y equals Z. There's only one inverse. So let's see if there's a sneaky, well, there is a sort of a sneaky, clever way to prove this, I think. We can prove it like this. Y is equal to y times the identity, because that's the definition of the identity. Multiply y by the identity, you get y. But you can also write the identity as x times z. This is y times xz, because E equals xz. And this is the same as yx times z, by associativity. And yx is E. Because, again, yx equals E. And E is the identity, so E times Z equals Z. So this equation says y equals Z. That's the end of the proof. And I can make the following very important observation, because the inverse of an element x is unique, we can write it as just x to the power minus 1. That means the inverse of x, and we just proved there's only one, that's unambiguous. So x times the inverse of x, or x inverse x times x, is the identity. This is the notation we use if we're writing the group operation multiplicatively. Additively, we write the inverse of x is an element we call minus x. So x plus minus x, or minus x plus x, is 0, if we write the identity as 0. This is when we use additive notation. Any questions so far? We're just going through the rudiments of group theory, just sort of the basic facts that are really fundamental and that one uses all the time. What's another? Well, let's say this is a corollary of what we just proved. So this is in the nomenclature in the text, corollary 2.1.3, that G be in the group capital G. Then there's an inverse, G inverse is in G. And what is the inverse of G inverse? G inverse inverse is G. So this operation of taking the inverse, if you do it twice, it brings you back to the element. And the proof is as follows. G inverse satisfies G times G inverse, and G inverse G equals the identity. Suppose I let, let's say, H be the inverse of G inverse. Then H would satisfy G inverse H equals HG inverse equals the identity. Or maybe I should write it in the opposite order. This is true, but let me just, so it looks, if I take H times G inverse, or G inverse times H, that's the identity. But, and there's a unique element that satisfies this equation. But G satisfies that equation. But at H equal G, I get the identity. So H is equal to G. Or in other words, the inverse of an element is the element. That's what I just proved. And again, all these things, when you understand what's going on, are quick and easy to write down. But to get to the point when you understand it, takes a certain amount of time and reflection. Okay. Let's look at some more properties of groups. These are all sort of the fundamental facts that one has to get to know. So this is proposition 2.1.4. Suppose we have a group and we have elements A and B in the group. Again, I'm trying to emphasize the fact that when you talk about the elements in a group, you could call them X, Y, Z, you could call them G, H, call them A, B, C. The notation you choose doesn't matter. Then I can multiply A and B. That's their product. And this element has an inverse. And it turns out that the inverse of the product AB is not the product of the inverse, but it's the product of the inverses in the opposite order. It's B inverse, A inverse. Proof. And these things are much simpler if the group is abelian, but we're not assuming that the group is abelian. So the order in which you multiply matters. So suppose I let X be B inverse, A inverse. Then what is AB times X? AB times X is AB times B inverse. Well, let me write it 2 steps. So this is going to be this by associativity. AB times X is A times BX. That's associativity. So this is A times B, and what is X? B inverse A inverse. And this, let me apply associativity to what's inside the big parentheses. This is B inverse times A inverse. Again, this is by associativity. But B times B inverse is the identity. This is A times the identity times A inverse. The identity times any element is just the element. And A times A inverse is the identity. So we just proved that AB times B inverse A inverse is the identity. What if I multiply in the opposite order? X times AB. Again, by associativity, this is XA times B. What is X? X is B inverse A inverse times A times B. Inside the big parentheses, I use associativity again. B inverse A inverse times A is B inverse times A inverse A. A inverse A is the identity. This is B inverse E times B, which is B inverse times B, which is the identity. So what this says is that X, B inverse A inverse, times AB is the identity. So here I have the element AB. I multiply it on the right by this, I get the identity. Here's the element AB. I multiply it on the left by the same thing, I get the identity. So that means this is just the definition of the inverse. The inverse of AB is B inverse A inverse. That's the proof. Any questions about any of this? I mean, this all takes really a lot of time sitting at home or sitting somewhere quiet and thinking, I think. Let me just recall something about functions. Suppose you have a function f from a set x to a set y. So we say f is 1 to 1. Or we also call this an injection or injective. If whenever x1 is different from x2, implies f of x1 is different from f of x2. So if you think of your set f going from set x to a set y, if you take two different elements, x1 and x2 and f, they get sent to two different elements, y1 and y2 and y. You don't have two different elements getting mapped to the same element in y. A function with this property is called 1 to 1. F is onto if for all y in y, there exists an x in x such that f of x equals y. So if you have this function from x to y, if you take any element in y, you can always find an element of x such that f of x hits y. And we say f is, and onto is sometimes called a surjection. All these words are superfluous. But f is a bijection if f is 1 to 1 and onto. It has both of these properties. That's called a bijection. So if we take the real numbers, f from R to R, defined by, let's say f of x equals x squared, this function is not 1 to 1 because f of minus 2 equals 4 and f of 2 equals 4. You're squaring. So minus 2 and plus 2. Here's 4. Here's 2. Here's minus 2. But squaring sends them to the same function. And f is not onto because f of x equal minus 1 is impossible, has no solution, right? X squared is never equal to minus 1 for any real number. So nothing gets mapped by this function f to minus 1, right? So the function f of x equal x squared is a very simple function, but it is neither one-to-one nor onto. Right? You take f of x equal to x plus 7, this is a bijection, because if x1 is different from x2, then f of x1, which is x1 plus 7, is not the same number as x2 plus 7, which is f of x2. And for any x, f of x minus 7, that's a nice number. What is that? That's x minus 7 plus 7, that's x. So f is onto. For any number x, there's some number that gets mapped to x. In this example, it's just the number x minus 7. So a bijection is a one-to-one and onto function. And proposition 2.1.5 says the following, that G be a group and let A be an element in the group G, the function, I'll call it L sub A of x, defined by L sub A of x is AX. So this is left multiplication. This takes every element x, the function takes every element x, multiplies on the left by A, is a bijection. And also the function R sub A of x, where you take an element x and multiply it on the right by A, so this is right multiplication, is also a bijection. And that's the proof of this. Let me give the proof in a couple of different ways. So if L sub A of x equals L sub A of y, that means AX equals AY. But this is multiplication on the left by A. And so if I take A inverse times AX, that's the same as A inverse times AY. But A inverse times AY is A inverse A times Y, which is the identity times Y is Y. And similarly, A inverse times AX, this is A inverse A times X, or E times X, or X. So X equals Y. That's what this long equation says. So L sub A is one-to-one. And if I choose any element x, L sub A of A inverse x is A times A inverse x, is A inverse x, is EX is x. So L sub A is onto. So this function is one-to-one and onto.
So can you move that up?
Oops, let's see. Yep. An equivalent way to describe a bijection is the following. So Suppose we have a function f from a set x to a set y, and we have another function g from the set y back to x. So we say g is the inverse of f if g composed with f. So we have a picture like this. Here's x, here's y, here's a function f from x to y. You also have a function g from y back to x, and you have a composite function, g composed with f, from x to x. So g is the inverse of f if g composed with f is the identity function on x. The identity function is just defined by, it sends the set to itself, it sends every element to itself. So g is the inverse of f if g composed with f is the identity on x. And also f composed with g, which is a function from y to y, is the identity on y. And f is a bijection if and only if, so f is a function from x to y, if and only if there exists an inverse function a function g from y back to x, such that these two properties are satisfied. G composed with f is the identity, and f composed with g is the identity. And the reason why having a bijection means there's an inverse, suppose you have a function f from x to y. So if I take any element in y, f is onto, so there's some element x which gets sent to y. So f onto implies that for all y in y, there exists x in x with f of x equal y. And f1 to 1 implies x is unique. You can't have another element x prime, say, which also gets sent to y. That's not possible because the function is 1 to 1. So every y comes from a unique element x. So we define g from y back to x by g of y equals x. So if a function is a bijection, it has an inverse. And it's also straightforward to prove that if a function has an inverse, it's a bijection. And we just proved that L sub A, left multiplication by A in a group, is a bijection. So it has to have an inverse. And I claim that the inverse function, I'll write it L sub A inverse, is L sub A inverse. This means left multiplication by A inverse. So where L sub A inverse of x means multiply x on the left by A inverse. So if I take L sub A inverse composed with L sub A applied to x, that's L sub A inverse of L sub A of x. That's L sub A inverse of AX. That's what left multiplication by x does. This is A inverse AX, and the A inverse and the A cancel. So it's the identity. This is X. So L sub A inverse L sub A is the identity on X. And similarly, L sub A inverse is the identity on, it's also like the identity on the group G, is also the identity on G. Okay. So we're just going through the very beginning bits of group theory, and it's all done very nicely in the beginning of chapter 2. Let's keep going. These are all fundamental properties. Solving equations. In the text, this is corollary 2.1.6. You can always solve an equation in a group.
We don't see it, Professor.
Sorry, thank you. Let G be a group. And let A and B be in G. You can always solve the equation uniquely. There exists a unique solution of the equation AX equals B in G. That is, this is an equation, find X such that AX equals B. I mean, this is what you did in elementary school. Solve the equation 6X equals 42, and you would say X is equal to 7. So here, but this is here we're solving this equation in the real numbers. Now we're in a group. You have two elements in a group, A and B, solve the equation AX equals B. And the statement is there's a unique solution to this equation. Well, one proof is, suppose I take the element A inverse B in G. A is in G, so A inverse is in G. B is in G, so A inverse B is in G. So AX is A times A inverse B. That's A inverse times B. That's the identity times B, which is B. So this is a solution. X equal A inverse B. And if Y is any elements in the group, and AY equals B, then if I multiply both sides by A inverse times AY is A inverse B. But A inverse AY is A inverse A times Y is E times Y equals Y. So Y equals A inverse B. That is, the only solution of this equation is A inverse B. So every equation of this type has a unique solution. We also have cancellation in a group. This is 2.1.7. Cancellation. So that A, X, and Y be elements in G. If AX equals AY, then you can cancel the A and X equals Y. If XA equals YA, You can cancel the A and get x equals y. And what is the proof? Well, ax equals ay. You can multiply each of these elements by A inverse, and A inverse AX is X, and A inverse A is Y. And the same here. If XA equals YA, then XA times A inverse is YA times A inverse. And the A and the A inverse cancel, you get X equals Y. And I want to make the following very important observation. AX equals YA does not imply X equal Y. You can't cancel the A if they're on opposite sides of the equation, right? Unless the group is abelian. But if AX equals AY, if A is on the left, you can cancel it. If XA equals YA, A is on the right, you can cancel it. But if AX equals YA, that does not imply X equals A, X equals Y. In a group, we have the multiplication table. Multiplication table of a group. It's just a way to write down what the group operation is. So let's see, let me see how I can describe this. Let G be a finite group. Finite group is a group that has only finitely many elements in it. Say G1, G2, G3 up to G sub n. What is called the order of a group, G, is the number of elements in the group. And we denote it with G with absolute value signs around it. Right? That's the order of a group. So if I write the group like this, the order of G is n. So I could write down a multiplication table. I write across the top the n elements of the group in order, and here vertically the n elements of the group are in order. Say this is G sub I down to G sub n, call this G sub j. And I fill in this table. Should have this line here. G1, 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 G2, G2, G1. It's where I have the element GI, and here the element GJ. In the table, in this box, if you like, I put in GI times GJ. So this is the multiplication table for the group. What's an example of a finite group? We can look at the congruence classes mod 3. Let me just write it. This is the congruence classes. We already studied congruence classes. Congruence classes modulo 3. you have the class 0 plus 3z, 1 plus 3z, 2 plus 3z. This is the set of all integers divisible by 3. Right, so 0 plus 3z, or just 3z, is 0, 3, 6, 9, 12, and also the negatives. Right, the multiples of 3. 1 plus 3z, this is all the numbers that leave a remainder of 1 when you divide by 3. 1, 4, 7, 10, 13. You also have the negative numbers, -2, -5, -8. Right? These all leave a remainder of 1 when you divide by 3. 2 plus 3z is all the numbers that leave a remainder of 2 when you divide by z. Divide by 3. And the negative ones, -1, -4, -7, and so forth. So this is a group with 3 elements. And if we write down the multiplication table, and in this case, we always call it a multiplication table. This is like the addition table. So 0 plus 3z, 1 plus 3z, 2 plus 3z. 0 plus 3z, 1 plus 3z, 2 plus 3z. What do you get when you add? 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 2 is 2. 1 plus 0 is 1. 1 plus 1 is 2. 1 plus 2 is 3, which is the same as 0, mod 3. 2 plus 0 is 2. 2 plus 1 is 3, which is 0. 2 plus 2 is 4, which is congruent to 1 mod 3. So for the group Z mod 3Z, this is the multiplication table, or the addition table, if you like. And if you look at this, you'll notice that in every column, you have each element of the group appearing exactly once. And in every row, you have each element of the group appearing exactly once. People tends to write this group as Z subscript 3. It's the same. Okay. And it's a homework problem that I'll go over on Monday, that in general, in any finite group, when you write the multiplication table, every column of the multiplication table contains each element of the group exactly once, and every row of the multiplication table contains each element of the group exactly once. These are like sort of basic facts. This is really a very important example because it generalizes to every n. So for every positive integer n, let Zn, or sometimes written Z mod nz, be the additive and abelian group of congruence classes modulo n. So Zn is a set of all classes of the form A plus NZ, where A goes from 0, 1, 2, up to N minus 1. So the cardinality of this group is equal to N. So for example, we already looked at Z3. Z4 is a group with 4 congruence classes, 0 plus 4Z, 1 plus 4Z, 2 plus 4Z, 3 plus 4Z. And the addition table, let me just write 0, 1, 2, 3, 0, 1, 2, 3, instead of writing the plus 4Z. 0 is the identity, so no matter what you add it to in whichever order, you get the same element back. 1 plus 0 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, which is the same as 0 mod 4. 2 plus 0 is 2, 2 plus 2 plus 1 is 3, 2 plus 2 is 4, which is 0, 2 plus 3, which is 5, which is congruent to 1 mod 4. 3 plus 0 is 3. 3 plus 1 is 4, which is 0. 3 plus 2 is 5, which is 1 mod 4. 3 plus 3 is 6, which is 2 mod 4. That's the addition table. This is a group of order 4. Let me give you an example of another group with 4 elements that's fundamentally different. Suppose I take rotations of a rectangle. Suppose I have a rectangle. Let me label the corners 1, 2, 3, 4. What are the symmetries? Rotations, I just mean symmetries. So I can take this rectangle and, of course, I can always do nothing to it. So don't flip it, don't move it, or change it by 0. So I'll call that the identity rotation. I could take this rectangle and rotate it around this horizontal axis. So then the top 4, 3 goes to the bottom, and the bottom 1, 2 goes to the top. So when I rotate this horizontally, I get the rectangle sitting like this. Let me call this something. I'll call it, I don't know, call it X. Or I could take this rectangle and 1, 2, 3, 4. I could rotate it around a vertical axis. And when I do that, the right side, the left side flips to the right side, and the right side flips to the left side. I'll call that Y. And the other thing I could do is I could take my rectangle, 1, 2, 3, 4, and I could pick it up and flip it around. So 3, as I can pick it up and rotate it, so I put the 3 over here. But if the 3 is here, then the 2, that's the short side, has to be there. And this is 4, and this is 1. So I'll call this Z. And these are the four symmetries of the rectangle. Actually, how can I get Z? I could have done the following. I could have taken my rectangle, flipped it horizontally to give me this, and then if I flip it vertically, the 2, 3 moves to the left, and the 1, 4 moves to the right. So Z is the same as X followed by Y. Or I could have done Y. I flip it vertically and then horizontally. It's also X, Y followed by X. Actually, let's look at the multiplication table for this group of symmetries. I called it a group. So you have to assume that I'm not lying to you when I say that. This is X. Sorry, E, X, Y, and Z. E, X, Y, and Z. So these are the four symmetries of the rectangle. If I take the rectangle and apply the identity symmetry, do nothing, and I do nothing again, E times E is E. E times X, I think of these as almost as sort of as functions operating on this rectangle. This means, like if you write yx, that means first apply the operation x, then apply the operation y. So this is composition of functions, just as you saw with permutations or as you saw in calculus. So E followed by X means you flip horizontally and then don't do anything else. That's still X. Or if you flip vertically and don't do anything and then just leave it fixed, that's Y. Or if you do the Z operation and then leave it fixed, that's Z. I mean, E is the identity, so XE is X, YE is Y, ZE is Z. But what is X times X? That's what goes in here. This means flip horizontally again, you're back where you started. That's the identity. If you flip vertically, and then flip vertically again, Y times Y, you're back where you started. If you perform Z, you do a horizontal flip, then a vertical flip, and then a vertical flip, which cancels the vertical flip, and then a horizontal flip, which cancels the horizontal flip. Z times Z is also E. So down the main diagonal of this table, we have the identity. XY, well, we just saw XY is equal to Z, and YX is equal to Z. We can fill that in. Here, we have XZ. What is XZ? So you apply Z, you get to this configuration. X is the horizontal flip. When you do X, you have 1, 2 on the bottom. You have 2, 1, and on the top you have 3, 4. That's exactly this. 2, 1 on the bottom, 3, 4. So XZ is equal to Y. This is, ZX. Actually, what I just said was XZ. So let me just, you do Z, you get to this configuration. You flip it horizontally, you're here. So XZ is Y. What about ZX? That means first you perform X. That means you have 1, 2, 3, 4. Then you flip it so the 2 is down here. But there's only one symmetry with the 2 down here, that's Y. So XZ is equal to Y. YZ, here is Z. Flip it around the vertical axis, that's Y. You have 1, 4, that's X. ZY here's y. Flip it so the 4 is down here, that's x. So this, miraculously, is the multiplication table for the group of symmetries of the rectangle. And this is a very different multiplication table from the multiplication table for another group with 4 elements, the group of congruence classes mod 4. In this multiplication table, we have the identity down the main diagonal. In this multiplication table, we do not have the identity 0 down the main diagonal. So these are really two fundamentally different groups. Groups that are the same are called isomorphic. And these two groups with 4 elements are examples of groups of the same size or cardinality that are non-isomorphic. And yeah, we'll talk about that a lot more on Monday. And also for Monday, I'll assign a few problems from the end of this section, and I'll post them on Blackboard shortly. Okay, so we covered a lot today, but this is what we're going to study for the entire remainder of the semester, the subject of group theory. And what we did up to this point, the number theory that we did, congruence classes, permutations, these are all examples of groups. And we want to study now the general concept of the general theory of groups. And what can we say about groups in general that will apply to all of the concrete examples of groups that we've studied? Okay. All right, that's a lot. Any questions about anything we've done up to this point? And then I think I'm going to stop here. I'm not, I can't be, there won't be a problem session today, but there will be problem sessions on Friday and over the weekend if you have any questions. Also, if you have any questions about the exam, and I will post those hours in a day or so. But there will be problem sessions on Friday and on the weekend. But at Friday, it won't be at 11 o'clock. It'll be in the afternoon. All right, any questions before we quit for the day? Okay, well, be well. Let me just see if there's something in the chat that I can look at. Can you explain how you did the other multiplication table? So I did 2 multiplication tables for addition of integers. This, I mean, for example, y is 1 plus 2 equal to 3. Because if you take a number that has a remainder of 1 when you divide by 4, and you add it to a number that has a remainder of 2 when you divide by 4, you get a number that has a remainder of 3 when you divide by 4. This is just an instance of the fact about congruences that we prove that if, I can write it like this, if x is congruent to A mod 4, and y is congruent to B mod 4, that implies that x plus y is congruent to A plus B mod 4. That's the only fact that I'm using when I construct the addition table. So if you have a number x, which is congruent to 3 mod 4, and y is congruent to 2 mod 4, for example, then x plus y is congruent to 3 plus 2 mod 4, which means x plus y is congruent to 5 mod 4. But 5 is congruent to 1 mod 4, so x plus y is congruent to 1 mod 4. Because 5 It's kind of going to 1. Mod 4. That's what I use there. Okay, well, we're done for the morning. Be back on the weekend.